Alright, y'all. Okay, so this video is going to have some applications of separable differential equations. Not by any means can you think this would be, I've exhausted every possible example of them. But these are pretty common ones that show up for separables. And one of them is a mixing problem. I'm going to start off with this one. It makes me fairly happy. Here's a pot. It's got a leak in it, or a hole in it, or a spout if you prefer. I don't really care. Now, notice that the water is draining out of this at a rate of, I'm going to say 5 gallons per minute. And in this pot, you've got salt. Well, I'm going to call it salt mixed with water. Salty water. And into said salty water, fresh water. Now, these mixing problems have been around for eons of time, and a lot of times they're actually fairly... You have to assume some things, always. You always have to assume some things. But here's the idea. When the water comes in, it mixes fairly thoroughly. This is a big enough tank, and you're only draining it at 5 gallons per minute. Oh, and by the way, filling it at 5 gallons per minute. What you're going to see is that obviously, first of all, the level will not change, but that the mix will be fairly uniform-ish. It kind of depends on the situation, and if you're in a specific, like say, chemical company's thing, there will be a situation where the thing is being mixed constantly. Like in this case here, it just says what's going in, but you could very well have a process where it's being mixed, or it could be being injected in here in such a way that it actually stirs it as it goes in. So when we say it goes in, we draw the picture like this. So, but don't get this idea that somehow it's just going around the top, or it's not mixing well. We're saying it's thoroughly being mixed. Okay. Now, I'm going to say that the salt amount, the amount of salt, is a function of time. So notice that this is amount of salt. Could be in anything. I'm going to call it in pounds, if you will. Okay, so initially, there's 100 pounds of salt in there. Which made it up. Okay? And this tank holds 300 gallons. It'll always have 300 gallons in it, but it won't always be 100 pounds of salt in that thing. Eventually it's going to be less and less and less and less and less. Okay? Funny story, when I was a kid, I remember this guy, the youth pastor at church, gave this thing. He's like, all right, here's this cup of water. Suppose you put, now granted I grew up out in the sticks, but suppose you put a little bit of cow manure in there. And you just let the water run into this cup, and eventually it's going to, clean the cup out. And everyone's like, yeah, you're right. It'd be pretty much, so after a while, it'll pretty much, there won't be any cow poo in it anymore. And you're like, yeah. Are you going to drink it? Oh, no. So the same thing's going to be true here. Clearly this thing is going to be tending to 0 pounds of salt. Technically, it'll never get there. So in your mind, what you might be thinking is, this sounds like an exponential decay problem, and to be honest with you, you're right. And so that's the idea. Now, what's going to happen here? Well, I've got ds dt, of course. And what's it going to be? Well, you're like, I don't know. Now, check it out. If you're putting fresh water in, are you putting salt in with the fresh water? No. Are you taking salt out by putting in fresh water? No. Now that's very hard for some people to get their mind wrapped around. No, it's doing something to it. No. But the drain is. So the drain is draining at 5 gallons per minute. That make sense? Times, okay, now I need to have this in salt, right? I need to have it in pounds per minute, because this is salt, so it's in pounds. Time, of course, is in minutes. So what I need here is something that's no, I want minutes to stay. I want it to be in pounds per gallon. And you're like, well, there's going to be some pounds of salt always, right? In how many gallons? In 300 gallons, dog. There it is. And so, of course, this cleans up to be ds dt of course, the gallons cancel, and you're left with negative S over 60, if you will. And at this point, I'm going to drop the pounds per minute, but that's what it needs to be in, because salt is in pounds and time is in minutes. Okay? Well, this is 100% separable. Any idiot can see that, right? So it's negative, well, I'm going to leave the negative over there. I'm going to have 1 over S. ds is equal to negative 1/60th dt. So ln of S is equal to negative t over 60 plus c. So S of t, of course, is c e to the minus t over 60. And once again, since I gave you that the initial amount was 100, and since this is a separable differential or an exponential equation, that is going to be 100 right there. So then the question would be, okay, well, when is it less than... So a question I could ask you is, how much is there after 10 minutes? Or, so, I mean, you could do it a couple of ways. I could graph this thing in Desmos. I could do, just actually solve it, whatever makes me happier. I don't know that I care this time. I think I'm just going to graph it. But, of course, I could always just, go for old-fashioned solving. Come on, graph it to me, you hippie. Start graphing. There we go. So 100 e to the negative x divided by 60. And give it the old projector mode and zoom out a ways. Of course, there you go. So then the question would be, when is it less than 10 pounds? I don't know. So a person could, of course, just y equal 10. And then come down here and find out. Boom, it's going to take it 138 minutes to get there. Okay, cool. You could find out, when is it less than, whatever, 0.002 or something. Maybe that's when it's going to be at small, it's when I can't detect it anymore or something. Hey, at 3 minutes, well, at 3 minutes there's still 123 pounds, or 95.123 pounds of salt left. So anyway, from there on out, it's pretty easy. The question is, how do I apply this stuff? And so these are pretty cool problems. Now, in a section that will be coming up in a few chapters, why that tank is going to cascade into another tank. What? Oh, and maybe into another one. And maybe, of course, we got water into here, and we got water out the bottom. Okay, whatever. We're going to see some of this later on. What tank feeds into this tank? Feeds into this tank. Feeds back into that. Shut up. No way. X, Y, and Z. We got water coming in. We got water. Oh, what a god-awful mess. Now, interesting to note in this situation here, right? Any of these situations, these are going to be systems because there's an X, a Y, and a Z. So they're going to get messy to have to solve them. The same thing's true here, X, Y, and Z. But they aren't going to be just a separable equation. Turns out the first one, this one, always is because it's just got one output. This one, not so much because you got an input and an output and an output and an output and whatever, okay? So this one's a little different, a little messier, but fun. This one, this top tank, will always be a separable situation. Not so much this one because it's a little different story, okay? But that's a pretty good example of one. Now, another one that I rather enjoy is someone that we did in physics last year. Here's a cup of coffee. Okay? It's got some initial temperature. The temperature is a function of time. Maybe T of 0 is that my coffee is 99 degrees C. I don't know. And maybe I know that after 30 minutes, it's down to 40 degrees C. I don't know. Just pulled that out of my hat. And so, that from there, last year we did Newton's law of cooling on this guy. Well, Newton's law of cooling in physics actually comes about from a differential equation. And it says this. It says that the rate of change of temperature with respect to time is proportional to the difference between, and I got hang on a sec here. I'm getting a call. It can be written several ways. I personally like to write it as ambient minus the actual temperature. Some books write it this way instead. I've seen it written this way too. Either way will work because clearly all you're doing is pulling the negative out front. This one's a little prettier to integrate for our purposes, but it's not bad because, of course, this is a separable differential equation. You notice there's no time in here at all. So I'm going to divide by this mess to the other side, and I'm going to get 1 over t minus a, dt, of course. D big T, stupid. There you go. Is equal to negative k dt. Okay? Now, if I left the negative in, it's going to be a minus t, and I'm going to have to do a substitution, and I'm going to get a negative du, and I'll get the same answer no matter how I slice it. But this is, I've always preferred to write it that way when I teach it in physics, but this one's a little prettier version of it, I think, when it comes to integrating. Okay? Now, let's check this out. So that's negative kt plus a constant is equal to the ln of t minus a. Not to say that you didn't use substitution right here. You just say u is t minus a, so du is equal to dt, right? So it's a 1-to-1 deal. It would have been negative if it had been a minus t, and it would have come out the exact same way. Exponentiate, you're going to get c e to the minus kt is equal to big T minus a, and so t of t is equal to a plus c e to the minus kt. Now, what happens if I leave my coffee sitting outside on a 18 degrees Celsius day, which is not cold per se, but it's fairly chilly? Why, my coffee is going to come down. I know this. I know it's going to start up here, but it's going to come down and it's going to approach, ambient temperature, right? Likewise, if it's a hot day and I take a cold drink outside, it's going to come up and it's going to approach it from the bottom side. Okay? So, not that big a deal. Now, you'll notice that there are the ambient temperature, so I didn't tell you that. So, let me just say ambient temperature is 18 degrees C. So, I can begin to fill in the pieces. Now, what you'll notice is I have two unknowns, C and this negative K business. Now, C is obviously going to have to do with something about ambient and the original temperature. I mean, you're going to see that in a second as soon as we get there. You'll be like, oh, duh. K is going to have to do with the coffee. Now, the cup, rather. If my cup is, this giant insulated cup and there's this little teeny tiny hole right there, well, it's not going to cool off very fast. If it's one of those giant soup bowls, that you get to sometimes the fancy coffee places where you can have all kinds of convection across the surface, and maybe this is like China thin little stuff. Oh my word, it's going to cool down like crazy. You're going to get a big K, small k, right? So this is going to cool off a lot smaller, a lot slower than this guy over here. But how am I going to find those guys? Well, from right here. You see that? From right there. Now I'm going to do t of 0 first. Now again, a person could come right up here. Boom. Check it out. Well, at 0, it's 99 degrees, right? So 99 minus ambient is equal to C e to the but it's e to the 0, so it's just equal to C. So check it out. What is that? 99 minus is 81, right? So that means this is going to be 81 right there. Oops, e to the minus kt. And actually, a lot of times in physics books, you'll see it written thusly. In a high school physics book, it'll just be written as ambient plus initial temperature minus ambient e to the minus kt. Okay, that's where that formula comes from, because that's exactly what it is up there. Okay. Now again, k, well, I'm going to get that from actually observing the problem. And so I've observed it was this initially, it's down to this later on, so let's plug that in. When t equals 30, we're going to be down to 40. Now, of course, it's going to look something like that. If I minus this, I'm going to get 22 divided by 81. What are you doing, stupid? Why don't you pay attention to what you're doing? Get out the old calculator. Boom. Boom goes the dynamite, yo. Boy, quit doing that. You know how to do this. You just go, whoop, whoop. There you go. Nice. Of course, you can hit solve, because Mr. Grimm does not care, but since I've come this far already, I'm just going to keep going. 22 divided by 81 is that. Of course it is. We'll take the ln of that. So I'm going to get the ln, of course, and of course I'm just going to leave it like that. That's the way my calculator does it, and it's just as easy anyways. So then just divide by negative 30 to both sides. Voila. And there's my k. Notice that my k better be positive because I already have a negative sign in front of it. A lot of times I don't even bother to teach it with a negative there because that's just it'll all come out in the wash when it's all done. Diamond, enter. It's 0.04. So this becomes my equation then. Right there. Notice if this negative hadn't have been here, then what I would have ended up with, of course, is fart. All right, go back. I would have ended up with that. Well, darn it. It would have ended up with that, which is the same thing, but if I had a positive k, then it would have come out to the negative 0.04. Okay? And then, of course, if I graph that guy, it's boom, boom, boom. 18, that's not 18, stupid. 18 plus 81 e to the negative 0.04x. Boom! Friends, check it out. Y equal 18. Oh, looky there. Ambient temperature. Okay? Again, it would have been the same thing if I'd had a cool drink on a hot day, but it would have come up and approached 18, the ambient temperature, from the bottom side. Okay? That's pretty cool. I mentioned this one the other day, that the force on a person falling through the air, that is, mass times acceleration. Well, in the past, it was just mg because we ignored air resistance. But now, not anymore. Minus k v. Now, if I do it like this, that is, I do it as if it was a first ordered. That means if I do it as air resistance is proportional to velocity. Okay, then it becomes this equation right here. Okay, and so because g is negative, velocity, you're falling downwards, so your velocity is negative, so it's minus and minus to plus. This is acting upwards, this is acting downwards. If you're actually falling, this is obviously bigger than this. However, there will come a time when they'll be equal. When they're equal, there will be no force acting on you anymore. There'll be a no net force. No net force, no acceleration. There's no way that the air resistance can be greater than this, otherwise you'd start falling upwards, and that just doesn't make any sense at all. Okay? So we know what's going to happen here. We know we're going to get some sort of and I can draw it any way, but here's some velocity up here, which is a terminal velocity. It's the fastest that we're ever going to travel. Something like that. Now, we could look at it as if it was a negative down here like this, but the idea is it's going to approach, you see, some value. And we talked about this the other day in the video, whether you watched it all or not, and I don't remember, and it's not really that big a deal. I divided by m to everybody. So it becomes an acceleration problem, which is not any better, it's just different. Okay? If you set this baby equal to 0, we see that when the velocity is equal to mg over k, this is your terminal velocity, because at that time, this thing will be 0. Okay? So, there it is. Now, obviously, when we do this, that we're going to see that come up in a second. Now, question is this a separable differential equation? And of course the answer is yes. So I'm going to treat this as all one number. So I'm going to divide by this mess. And so, oh geez, I can't do that in my head. So I'm going to say g minus k over m v equals u. So du is going to equal negative k over m, right, dv. Well, I don't have k over m dv, right? So what I have then is I have just a dv. So I need to do negative m over k du. True that? So this right here, this whole side is going to become negative m over k, 1 over u, du. Okay? So that's negative m over k, ln of what's inside, which is g minus k over m v, right, equals t plus a constant. Now, let's see what happens. Well, if I solve this thing, I'm going to multiply by the reciprocal. So negative k over mt plus a constant. I think I'm just going to leave that as just a constant this time. I may come back and decide that I don't like that and change it in a few minutes. That's my prerogative, dog. I'm going to exponentiate both sides, so I'm going to get c e to the minus k over mt is equal to g minus k over m v. Right? Right, Mr. Groom. So, g minus c e to the minus k over m t equals k over m v. And now multiply 3 by that. So you're going to get m g over k minus, and that's going to be m times c over k. In other words, just a great big fat c. Okay. E to the minus k over m t is equal to some velocity. Okay? This is some velocity at time equals t. Okay, now that's true in general, friends. That's true in general. Now, let's say I've done some experiment and I realize that my k up here is 0.1. Again, I pulled that out of the Magic Pez dispenser. We're going to do an experiment in the next couple of weeks where we mess with this. You're going to get some actual data to approximate for k. Okay, but for right now, I'm just going to say, I think that's what I want k to be. So 0.1. And I'm going to say the mass of this beast is 50 kilograms. I don't know. Why not? Okay? So it's going to be 50 times g over 0.1 minus c, and this is going to be e to the minus, and it's going to be 0.1 divided by 50. .002 minus 0.002 t is v of t. True dat? True dat. Now, if I say to you, hey, look, at t equals, at t equals 0, my initial velocity was equal to 0, let's say, right? Because I'm just coming out the airplane and I don't have any downward velocity initially. Well, okay, so 0 equals, now what's going to happen here? Well, this is e to the 0, which is 1. And then this is really 500 g right here, right? True. So you're going to get, so then c is going to equal 500 g, whatever that is, all right? So 500 g. So what's going to happen then? Well, 500 g. Okay. So if I were to graph this thing, of course you can multiply that out. I think I will. Actually, I think I will do that over here in Desmos. I'm going to write it a little differently because I'm feeling a little lazy. So I'm going to go 500 times 9.8. Parentheses 1 minus. There you go, stupid. E to the try again. There you go, baby. That should do the job. Now, remember, initially, where are we? Okay, well, initially we had 0 velocity, correct? But where does this thing headed towards? Well, I don't know. Well, if we come up here a ways, we will see where it is supposed to be. Maybe if I zoom out, it'll be faster to get there. Come on. Come on. Come on. Whee! There it is. Do you see it? Nice. Why is it right around now? 5,000, of course, does not make any sense for this, okay? Because the 0.1 that I just randomly pulled out, not a true statement, okay? So that's why it's a little strange. So we're going to be doing this in a few days, again, coming up with some numbers that really make a lot of sense. But think about this. We already know what our terminal velocity should be. A terminal velocity, if you recall, was mg over k, right? So that's 50 times 9.8 divided by 0.1, which is 500 g. That's your terminal velocity. And it makes 100% awesome sense, because what happens? As t goes to infinity, what happens to this guy? This piece goes to 0, yes? And voila, there's your terminal velocity. Okay? So we'll monkey with these a little bit in the next few days. You're going to see them. It's going to be a good time. Of course, he also said, I want to do one more mixing problem, but this one's a little different, so pay attention. This time it is pure water. But this time we are dumping in salt. Now you're like, just pure salt, Mr. Groom? Maybe. Or maybe I'm putting in a certain percentage of salt in the water, right? So I think that's what I'm going to do. I'm going to put in salt water. That is, I'm going to say it's 30% salt by I guess by mass or by volume. I don't really care. It's not important to me. I'm going to say by volume. But I don't think it's really that big of a deal to me. Okay? I'm going to have water coming out at some rate, 10 gallons per minute. I'm going to have water going in at 10 gallons per minute. So here's my question. How much salt is going in per minute? Well, I don't know. It's 10 gallons per minute. And I'm going to multiply that by 30%, right, of 1 gallon, or I'm sorry. 30%, it's a 30% solution, right? 30% solution is going in, and of what? Well, I need to get rid of, that is, of salt per gallon. Does that make sense? So we're going to get points. So we're going to get 3s, right, per minute, right, or 3s per minute. I'll say that. So 30% of salt. Yeah, 30% of salt. Let's do by volume. So we're doing 3 salts per minute, I guess is what we're going to say. Okay. Yeah. I think that's how I want to phrase it. Now, coming out, we're going to be taking some out as well, right? So it's however much we have in there. So this tank, let's say this tank holds 100 gallon. Okay. Well, there's S amount of salt, right, per 100 gallon, right? So so coming out, we're going to have S over 100. This is in, pounds or salt or whatever per 100 gallon. And we're going to multiply that by 10 gallons per minute. And they cancel out. And so I'm going to be left with 10 over 100 is 10. So I'm going to be going in at this rate. Right? I'm going to write it like that for right now so you can see that per minute. Minus 10s. I'm sorry, no. I'm sorry, minus, it's S over 10. Like so. Okay? That's the idea. Now, what's going to really happen is we're not going to include the per minutes. Okay? We're just going to leave that off. So it's going to be 3s minus S over 10. And this is my ds dt. Again, on the previous problem, we were putting no salt in. So we didn't have it. We just had salt coming out. But this one's got some coming in and some coming out. Now, what's going to happen here? Well, eventually this thing is going to get up to, the saltiest it's ever going to be is 30% salt. Right? So in other words, that's the most that you're ever going to get into there. When I say 30%, maybe I should have, I don't want to say 30%. I think I'm going to stick with the 30%. I think that's what I'm going to stick with for right now. Now, again, we could do this with like antifreeze. If you're one of the kind of people that buys 50-50 antifreeze, I don't. I find that to be a complete joke. Here, buy half a gallon of antifreeze and a half a gallon of water, and we're going to charge you the same price as if you bought a gallon of antifreeze and mixed it yourself. It annoys me beyond belief. Now, yes, 50-50 is basically the ratio that you want, but over the course of a year, I leak some out, boil some off, whatever, and I add some water and some antifreeze throughout the course of the year. But I don't get serious about my antifreeze until about November, December. It starts getting cold. I check my antifreeze, and I want it to be protected down to a certain level. Well, it never is. It's never down as far as I want. So what do? Well, if I add 50-50, I'd have to pretty much drain the system out in order to add enough 50-50 to get the concentration up to 50-50. But if I'm adding 100%, I don't have to add as much to blend it up to that higher level. But again, the most salt we're ever in there is like a 30% blend. Okay, that's just what's going to boil down to. Okay, and so kind of keep that in mind as we're going along. That is why, God help me, I absolutely love mathematics in this regard, because it is so duh. And what's going to happen here is this. Well, you're just going to go, I factor that out, and then you're going to go, well, Mr. Groom, isn't that just 2.9? You're not wrong. dsdt. Hey, check it out. It's pretty cute. So you're going to flip it over to here, and you're going to get 1 over 2.9, or 1 over s, 1 over 2.9. That's a cute trick. ds is equal to 1 over, or equal to 2.9 dt, like so. And then away you go from there, right? And it makes a lot of sense in that regard. I think it makes a lot of sense in that regard. But hold up. I made a little bit of a boober over here. Maybe just a skosh of a boober. Well, hold that thought a minute. I gotta think about this. I changed my mind just a skosh on this. Let's don't say 30% salt. Let's just say 3 pounds per gallon of salt. I think that's how I want to do it. 3 pounds per gallon. Right, 3 pounds per gallon. So 3 pounds per gallon. That's a constant. That's not going to change. And so, actually, I could have probably just left it alone, but that's not going to change. It needs to be just 3 right there, and that's kind of a big deal. Now, I knew I was wrong as soon as I got to, right here. I'm like, wait a minute, I did something wrong. I have to go back and think about that for a moment. And then it was like, oh, duh. This has to be a constant because you're constantly putting in the same amount. If there's an S there, that leads you to believe that amount's going to change, but it's not. I'm putting the same amount in every minute. Okay, we're putting in 3 pounds of salt every minute. Okay, so that's kind of a big deal. What is going to happen here? Well, this is just going to be, salt as a function of t is going to be something like this. Oops, e to the 2.9 t. That means I'm getting an exponential amount of salt, but that's not happening. It's approaching some finite level. It has to be approaching. Okay, now this should work. So again, treat that as one big number. S over 10, not 5, you idiot. Okay, ds. There we go, is equal to dt. Some of you, not me, would factor a negative out of this so that there's no negative in this mess over here. You're darned if you do, you're darned if you don't. You're just as equally likely to screw it up either way, I think. So just try it. If you like it one way better, then knock yourself out. I don't care. True that? True that. Right? So this is negative 10, 1 over u du equals, the integral of dt. There we go. Okay? Which, of course, is t plus a constant. Negative 10 ln of u, which is this mess. Right? Right. Multiply by negative 10 to both sides. exponentiate. I don't know if you're picking up on this or not yet, but this whole E is going to show up a lot in differential equations. Which, by the way, is perfectly cool because he's a really cool dude. E is. We really like E. He's one of my favorite people. Okay? Wait, stop, hold the phone, brah. You're saying I'm putting in 3 pounds of salt per gallon. Bro! 3 pounds of salt per gallon. Interesting, interesting. So, down here, somewhere, down here, we should end up with a certain amount that makes sense to us as we go along. I have a 100-gallon tank. It should be coming in. It should come out right when we figure this mess out. And we'll see kind of how it works as we go along. But it feels pretty good so far, I think. Now, what happens here? Well, if I did I know initially how much water was is pure water? How much salt was in the tank initially? S of 0 was 0. Meaning that what had to be true? Well, if this is e to the 0 is 1, then this must be, C must be 30. And away you go. Okay? And a problem like that's kind of a slick deal. Okay? Obviously, as time goes to infinity, this is going to go to 30. Okay? And away you go like that. Okay? So that's 3 pounds of salt per 3 pounds per gallon. Oh, for God's sakes. Then that would have been 30 right there. Do you see that? Which would have made this 30 right here. Do you see that? Which would have made this 30. You see that? Which made it this 30 and that 30, but didn't affect anything over there. Which would have made this 30, which would have made that 30, which would have made that 30, which would have made that 300, which would have made then this would have had to have been 300 as well. Now, how did I know I was wrong? Because I was putting in 3 pounds of salt per gallon. Eventually, 100 gallons, I should have 300 pounds of salt. And what's going to happen here? As t goes to infinity, right, then my salt is approaching 300. And we can graph that and see, just for fun, boom. Boom goes the dynamite. Yes, wow. Yeah, maybe we should back out just a skosh. Oh, that was pretty cool. Let's change our x value from 0. 0 to, it didn't take very long, friends. Clear. 7. I don't think I even need 7. Oh, that's nice. Nice. So there it goes. Okay. And where is it approaching? Boom, it's approaching 300 pounds of salt. How long does it take to get there? Hey, not very long. Not very long at all. Now, clearly, if you're putting in more salt, like for instance, had this been 7 pounds per gallon, then we would have had 70, blah, 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 700 and whatnot. Then really all it would have changed, how would that have changed my problem over here? Wouldn't have changed it much. That would have become a 7. And this would have become a 7. It just shifted it up. Well, how am I going to change how fast it moves? I bet if you did this. What? In other words, if you put it in, if you put the salt in slower, okay, then it's going to then obviously take longer to replace it all. Okay, so can I keep that in mind as we're doing these things? Like the change of how much salt concentration-wise you're putting in is not really going to change how long it takes. It may take a skosh longer to get up to that high of a concentration, but not a lot. But if you say, let's just drain it in slowly, then obviously it's going to take a lot more time. Okay. I think that pretty much finishes up section 1.2. So by the time you're done watching this video, you should be good to go with everything from 1.1 and 1.2. I hope. That's the plan anyway. Boop. Boop. Stop.